I'm out here enjoying another glorious sunset, and it got me thinking about how the sun is about to disappear below the western horizon, and in a few hours, it will reappear above the eastern horizon. Where does it go when it disappears? And why do we have day and night and seasons? And what's the deal with shadows? Let's find out together in this episode all about Earth's motion. You may already know a bit about space and the movement of Earth, but imagine hundreds of years ago when people were just coming up with the best answer they could with the information they had, just like we do today. The only difference is all of the discovery that has happened between then and now. Every day, we can see the sun rise in the east, if you're up that early, and set in the west. We can also see other objects in the sky follow a similar pattern. Originally, we thought of the Earth as a stationary object, around which all of the other observed objects in the sky moved around. With that idea, we tried to develop models to try to help us understand something as enormous as space. Models are just a way of representing a system of ideas that help us identify and understand patterns that we observe. This original theory of a stationary Earth led to a geocentric model. If you break that apart, you have geo for Earth, and centric for center. The geocentric model actually explained a lot of the things that we see in the sky, especially with the naked eye. Things like the apparent motion of the sun and the stars. But there were understandably problems with this geocentric model. Let's dive a bit into that apparent motion I just mentioned. Imagine with me that you are driving along in a car through a wooded area. If you didn't know better, you might think the trees are flying by your car when you look out the window. Trees aren't stampeding by your car. We know that it is you who are moving relative to the surface of the Earth. This is the difference between apparent and actual motion, what is actually moving, and what appears to be moving based on your perspective. So, with further discovery, astronomers came up with a new model, the heliocentric model. In this model, the Earth and all the other planets revolve around the sun. Helio means sun. In this model, the sun is the stationary object. Great, but why does it seem to be moving across Earth's sky every day? The movement of the sun across the sky is not actual motion, it's apparent motion due to Earth's rotation. Earth spins around an imaginary vertical line that runs from the North Pole to the South Pole, a motion called rotation. The Earth completes one rotation or one complete turn about every 24 hours. This rotation is what makes the sun appear to move across the sky. If you're on the side of the Earth facing the sun as it's spinning, it's day. And if you're on the side facing away from the sun, it's night. You can measure this movement by observing shadows. Right now, the sun is over here in this direction, and my shadow is off in this direction. If I turn around, my shadow doesn't change and is still in this direction. That's because the sun is radiating light on the ground, and by standing here, I'm blocking the light from hitting the ground. Over time, our shadows do change direction and length. Let's try to observe this change throughout the day. You can try this too. All you need is a sunny day and something to cast a shadow. I'm going to use this lab stand, but you can use a pencil, a marker, a stick that has fallen off of a tree in your backyard. Whatever you use will have to be placed in an area that is going to be sunny all day. Your item will need to be stood up straight, so you can use clay or tape to stand it up or just place it in a stand. And lastly, you will need some sidewalk chalk. I am going to trace my object shadow 5 different times today so that we can see how its shadow might change throughout the course of the entire day. If you're still here liking this video, let us know and hit that subscribe button so you never miss an episode. As you can see, our object shadows followed opposite the sun, with shadows longest in the morning and evening and shortest in the afternoon when the sun was directly overhead. As the Earth is both revolving and rotating, it's not sitting straight up and down. Its axis is actually tilted. This tilt causes one part of the Earth to lean a bit toward the sun, while another part of it is leaning a bit away. This lean causes different parts of our planet's surface to get more or less sunlight and heat. As the Earth travels around the sun, these differences create a pattern throughout the year that we call seasons. When the northern hemisphere, this part north of the equator, is tilted toward the sun's rays hit it at a higher angle and for longer periods of time, which means it gets more energy from the sun. The combination of this increase in solar energy and the longer periods of sun exposure creates summer for the northern hemisphere. That's why in summer, temperatures get warmer because the days are longer and the sun is more intense at that angle. When the northern hemisphere is tilted away from the sun's rays hit it at a lower angle and for fewer hours of the day. The result is winter, so cooler temperatures because of the shorter days and less intense sunlight. As you can see, the northern and southern hemispheres are always in opposite seasons. When the northern hemisphere is tilted toward the southern hemisphere is tilted away. Spring and autumn are the seasons when the Earth is transitioning between the two extremes of summer and winter, either warming up from winter or cooling down from summer. One quick thing to note. The heliocentric model considers the sun as stationary, but the sun is actually just one star of billions orbiting the center of our galaxy. So it's important to know that our sun, along with the rest of our solar system, is moving. Go check out your shadow, or be sure to appreciate Earth's rotation during sunset this evening. And if you want to learn more science, you can check out this video next.